Good morning, everyone. Thank you for joining us today. In our last deep dive, More Than a Machine, we really got into the philosophical and definitional side of things, the why of robotics. Well, today we're popping the hood. We're moving from the abstract to the tangible, from the why to the what. We are going to dissect the fundamental building blocks of a robot, its core anatomy. So if you're ready to get your hands virtually dirty and see what makes these machines tick, let's jump right in. Okay, so here's our game plan. First, we'll lock down the single most important principle in all of robotics. Then we'll break down the robot's operational cycle into its three key stages: how it senses the world, how it thinks about it, and finally, how it acts. And to wrap it all up, we'll synthesize everything to see the complete unified anatomy of a robot. All right, let's start with the absolute bedrock. There's a concept so foundational, it's essentially the universal grammar of robotics. It doesn't matter if we're talking about a Roomba bumping around your living room or the incredibly complex Canadarm2 assembling the International Space Station, they all speak this same core language. Understanding this one principle is the key to unlocking everything else. So that brings us to the core question of this entire field. What is that single foundational paradigm that every single robotic system is built on? If you strip away all the complexity, all the different hardware and software, what is the operational blueprint that remains? This is it, the key that turns a pile of parts into a functioning robot. And here it is, the sense, think, act cycle. This is the heartbeat of every robot. It's a continuous, repeating loop. First, the robot senses its environment, gathering data through its sensors. Then, it thinks, processing that flood of data to make an informed decision. And finally, it acts, executing that decision physically in the real world. Sense, think, act. It's that simple and that profound. This loop is the central theme for our entire discussion today, so keep it front and center in your mind. So, with that cycle in mind, let's dive into that first critical step, sensing. You see, a robot without sensors is basically just a dumb machine. It's blind, deaf, and completely unaware, just repeating pre-programmed motions in a void. Perception, the ability to sense reality, is its only connection to the physical world. It's what elevates a machine from a simple automaton to an intelligent system. So let's explore how they do it. Robotic senses really boil down into two major categories. On one hand, you have exteroceptive sensors. Think of these as the robot's outward-facing senses, just like our own eyes and ears. They gather information about the external world, things like vision with cameras or distance with LiDAR. On the other hand, you have proprioceptive sensors. This is the robot's sense of self. It's how it knows the position and orientation of its own body parts, like where its arm is or how it's balancing. Both are absolutely critical. This table gives us a great look at the heavy hitters in exteroceptive sensing. Let's start with the camera. It's the closest thing to our own vision, providing rich color and texture data. But its big weakness? It's terrible at judging depth on its own. So we get clever. We either use two cameras for stereo vision, mimicking our two eyes, or specialized time-of-flight cameras that actively measure depth. Next is LiDAR, which stands for light detection and ranging. This is the tech you see spinning on top of autonomous vehicles. It shoots out millions of laser pulses per second and times how long they take to return. The result is an incredibly precise 3D map of the environment called a point cloud. It's like seeing the world's raw geometry. And finally, we have radar. Its superpower, as the table shows, is its ability to work in almost any weather. Fog, rain, snow, no problem. It sends out radio waves and can even directly measure the velocity of other objects. Its trade-off is lower resolution compared to LiDAR. Now, here's the crucial part. No single sensor is a silver bullet. The real magic happens with sensor fusion, where the robot's brain combines the strengths of all three. The camera provides color, LiDAR provides precise geometry, and radar provides all-weather velocity data. Together, they create a robust, multi-layered perception of the world that is far more reliable than any single sensor on its own. Okay, now let's turn inward to the robot's sense of self. The most fundamental proprioceptive sensor is the encoder. You'll find one on every single joint of a robotic arm. It's a high-precision device that constantly reports the exact angle and speed of that joint back to the brain. It's how the robot knows precisely where its limbs are in space at all times. Then you have the IMU, or Inertial Measurement Unit. This is basically the robot's inner ear. It combines accelerometers and gyroscopes to give the robot a sense of its own motion, orientation, and balance. When you see a robot like Boston Dynamics' Atlas doing a backflip and sticking the landing, that's the IMU doing some seriously heavy lifting. Finally, you get into the sense of touch with force/torque and tactile sensors. These allow a robot to feel how hard it's gripping or pushing, enabling it to perform delicate tasks like handling an egg without crushing it or inserting a key into a lock. So, we've got this massive stream of data pouring in from all these sensors. What happens next? Well, now we move to the second stage of our cycle, think. This is the robot's brain, this central processing unit, where raw, meaningless data is transformed into intelligent, actionable commands. This is the bridge from perception to action. Let's take a look inside the robot's mind. A modern robot's brain is really a two-part system. First, you have the robot controller. Think of this as the robot's brainstem or nervous system. It runs a real-time operating system, or RTOS, and its only job is to handle the low-level, high-speed calculations for motion control. It's constantly solving complex kinematic equations to figure out the exact signals to send to the motors. It has to be incredibly fast and deterministic. Then you have the processing core. This is the cerebrum, the seat of higher cognition. This is typically a powerful computer with a CPU and, increasingly, a GPU. It's where the big picture thinking happens, running AI models to interpret camera feeds, executing path planning algorithms, and managing the overall system, often using a framework like ROS, the Robot Operating System. The processing core makes the plan, and the robot controller executes it with microsecond precision. Now, for any robot that moves, there's a classic chicken and egg problem. To navigate a space, you need a map. But to build a map, you need to know where you are. So how do you start from nothing? The answer is an elegant and powerful algorithm called SLAM. As the definition says, it stands for simultaneous localization and mapping. It's a process that allows a robot to be dropped into a totally unknown environment and, as it moves, build a map while simultaneously figuring out its own position on that map it's building. It's the foundational algorithm that makes autonomous navigation possible. So how does a robot achieve that superhuman precision we see? It all comes down to something called a feedback control loop, and it is the very essence of the think process in motion. Let's walk through it. The robot wants to move a joint to a specific position. First, it senses its current position using the encoder. Then, in the think phase, it compares where it is to where it wants to be and calculates the error. Based on that error, it computes a new motor command designed to reduce that error. And finally, it acts by sending that command to the motor. The key here is speed. This entire loop happens thousands, sometimes tens of thousands of times every single second. It's a relentless cycle of sense, compare, correct that allows a robot to maintain incredible accuracy. Okay, we've covered sense and think. Now we get to the final and perhaps most satisfying part of the cycle, act. This is where digital decisions become physical reality. It's where the rubber meets the road. If sensors are the eyes and the controller is the brain, then actuators and end effectors are the robot's muscles and hands. This is how robots physically change the world around them. So what gives a robot its motion? The answer is actuators. As the slide says, they are the robot's muscles. Their job is to convert electrical control signals into physical motion and force. Now, there are different types, like hydraulics for heavy lifting or pneumatics for quick, snappy movements. But in the vast majority of modern robotics, the undisputed king is the electric motor. They're precise, efficient, and incredibly versatile. Within the world of electric motors, two types dominate. Stepper motors are simple and cost-effective. They move in discrete, fixed-angle steps, which makes them great for open-loop systems like 3D printers, where you just need to command a specific number of steps. But for robotic arms, the true workhorse is the servo motor. The key difference is that a servo is a closed-loop system. It has an encoder built right into it, providing that crucial feedback. The motor always knows its exact position, allowing it to move to and hold a precise angle with incredible accuracy and torque. This is why it's the go-to choice for almost every robotic joint. A robotic arm is just a manipulator. Its true function is defined by what's on the end of it. We call this the end effector, or end-of-arm tooling. This is the robot's hand. As you can see, this can be a huge variety of things. It could be a gripper, a simple parallel jaw, a complex adaptive hand, or even a vacuum cup. Or it could be a highly specialized tool. The same robotic arm can become a welder, a paint sprayer, a drill, or a scanner simply by changing its end effector. The tool truly defines the task. For a truly mind-blowing example of actuation, look no further than the Da Vinci's surgical system. This is where robotics becomes an extension of a human expert. A surgeon controls the robot, but the system isn't just mimicking their movements, it's enhancing them. First, it completely filters out the natural tremor in a surgeon's hand, resulting in perfectly steady motion.
Second, it can scale the movements, so a 1-inch move by the surgeon translates to a 1 millimeter move by the tool inside the patient. And finally, its wristed instruments have a greater range of motion than a human wrist, allowing for incredible dexterity in tight spaces. It's the ultimate human-robot partnership. And there we have it. We've journeyed through the entire cycle, from the sensors that perceive the world, to the brain that processes and decides, to the actuators that carry out the actions. We've seen how each piece plays a vital role. Now, let's bring it all together and distill this down to the most important takeaways.
So, after covering all this ground, from sensors to SLAM to servos, what is the single most important thing to remember? If you walk away with just one concept that defines the anatomy of a robot, what should it be? And this is it. The key takeaway is that every single robot, no matter how simple or complex, operates on that universal sense, think, act cycle. It is the foundational triad. If you can understand how a system is sensing, what it's thinking, and how it's acting, you can understand any robot you encounter. It's the elegant, powerful principle that governs this entire field, and it's the foundation upon which the future of robotics is being built. I really hope you enjoyed this deep dive into the anatomy of a single robot. If this piqued your interest, you'll definitely want to join us for our next session. We're going to scale up from a single robot to an entire factory, exploring the factory's nervous system. We'll get into the world of PLCs, SCADA, and industrial control systems, the technology that makes massive, automated manufacturing possible. It's going to be a fantastic session.
Thank you so much for joining us today. I had a blast breaking this down with you. If you want to keep exploring the frontiers of technology and AI, make sure you subscribe to our channel, Tech, AI, and Beyond. We've got a ton of great content planned. Until next time, stay curious.